you'll give the hand signal. Okay. Ladies and gentlemen, please rise. Announcing the arrival of Yang Bahagia Profesor Dr. Nosada Abdul Rahman, Timbalan Naib Chancellor Pendidikan and Inovasi, and the arrival of Professor Dr. Bernardine Wong Cheng Kiat. Ladies and gentlemen, please be seated. First of all, a very good afternoon to Yang Bahagia Professor Dr. Nosada Abdul Rahman, and of course Professor Dr. Bernardine Wong Cheng Kiat, Yang Berusaha Dekan Profesor Zana, and Ketua ISM, Professor Wan Ainun, Datuk, Datin, distinguished guests, management of the Faculty of Science, University of Malaya, and ladies and gentlemen. It's my pleasure to welcome all of you to the inaugural lecture by Professor Bernardine Wong, entitled Quantum Theory and the Atomic Nucleus. Without further delay, I would like to invite the chairperson for today's inaugural lecture, Professor Dr. Nosada Abdul Rahman, please.
Assalamualaikum warahmatullahi wabarakatuh. Very good afternoon, ladies and gentlemen. Professor Dr. Bernardine Renaldo Wong Cheng Kiat. Professor Dr. Bernardine Renaldo Wong Cheng Kiat studied in the University of Malaya and was awarded BSc in Science, second upper honors in Physics in 1980, MSc in Physics in 1983, and PhD in the field of nuclear reaction theory. After serving as an instructor at the PJ Community College from 1988 to 1993, he joined as a lecturer in December 7th, 1993, and was promoted to associate professor in 1999 and subsequently to professor in 2006. Professor Bernie Wong, as we know him, has over 30 years of undergraduate teaching experience, primarily in mathematics, physics, and engineering courses, with focus on the use of computational methods. He has developed and promoted the use of Excel, MATLAB, Fortran, Mathematica, and C++ software in teaching and research, and has taught computational mathematics at postgraduate level in engineering faculty. Professor Bernardine has 35 years of experience in theoretical physics in the study of nuclear reaction processes caused by the interaction of heavy nuclei. He has published 50 papers in local and international journals, as well as in conferences and proceedings. His research has been supported by IRPA, SAGA, UMRG, and the LITER program, and his research has also received bronze medal at Research Invention Innovation Expo in 2005. Professor Bernardine Wong has been invited to present invited talks at international conferences. To date, he has 5 PhDs and 5 MSc degrees, which has been conferred under his supervision. He currently supervises 2 PhD candidates and has received various excellent service awards from from the year 2000 for the year 2003 and 2006, as well as excellent service certificates for the years 1998 and 2007. Professor Bernardine has held administrative position at the International and Corporate Relations Office as Deputy Director from September 2007 to January 14, 2010. In this role, Professor Bernardine has served to build linkages between and other higher education institution of international repute. He has served as acting director for Kongzi Institute for Teaching of Chinese Language from January 15, 2010 to October 31st, 2010, to promote the teaching of Mandarin to Malaysian public. From January 2010 to January 2013, he was the director of the University of Malaya Center for Continuing Education, or UMCSET, where his role is to develop it into a center of excellence in the field of continuing education through the provision of courses and certificates and executive diploma level. During his tenure at UMCSET has been recognized as an academic responsibility unit or center, which offers accredited executive diploma programs to the public via the self-accreditation mechanism of Professor Bernardine has led UMCSET in the development and provision of full-time diploma programs, which was released in 2013. And he has assisted in the establishment of Private University of Malaya since January 2010 to realize the International University of Malaysia Wales, or IUMW, which has now been established and operates at the City Campus, Jalan Tun Dr. Ismail. He also served as the Vice President Academic Research and Internationalization from January 2013 to October 2014. And during his tenureship, 30 programs have been approved. Professor Bernardine worked with colleagues from University of Wales to lay the groundwork for the dual degree program and assisted the president or CEO of the IUMW, to ensure that IUMW becomes an exemplary and innovative international higher education institution. He is the member of the Board of Governor of University IUMW, as well as Board of Manager for La Salle School, Brickfields, Kuala Lumpur. And since November 2014, Professor Bernardine has resumed his role as a professor at the Institute of Mathematics Science in University Malaya. So without further ado, this afternoon I'm sure you would like to hear him speak more than me. I would like to invite Professor Bernardine Wong to give his inaugural lecture entitled Quantum Theory and the Atomic Nucleus. Please.
Thank you, Prof. Nur Saada, our Dean, Prof. Zana, Head of Department, Dr. Wan Ainon, colleagues, friends. As I look out here to all of you, I'm really grateful for the blessings that God gives, for giving me this opportunity to give this lecture. It's called an inaugural lecture. But I was promoted about 10 years ago. If anything, it probably inaugurates retirement, which will come in about 1 week's time. But I am a true born academic, and I don't think I stop just because I do not officially belong in the university in the tenure as a staff. I would like, before I begin, to just acknowledge a few people, if I may. I'm going to be speaking about quantum theory, and I learned a lot of my quantum theory from Emeritus Professor Dr. Chia Swee Peng, who's seated here near the front. So I'm grateful to Prof. Chia. And I know that if I say anything that's not quite right, I'll see it immediately. I'm grateful also to my friends who are here, who were former classmates of mine with me here in the physics department from 1977 to 1980. Thank you for being here as well. And friends, and among them, one who was a colleague for many years, Professor Kwek Kwan Hyang. I'd like to thank also all the some of the retired staff of ISM, who I had the great pleasure of working with and learning from over the years. The introduction just now said that I worked for 5 years at PJ Community College, and I'm especially thrilled that my first boss, Dr. Ludasamy, is here in the audience, and I'm grateful to that. And also grateful that I had the great good fortune here in the university to be part of an exciting initiative that University of Malaya forms a private university. And I have my latest boss, Prof. Hamza Abdul Rahman, who was president and CEO of IUMW. Thank you, Prof. Hamza, for being here. I am speaking about quantum theory and the atomic nucleus. And as I look at the audience here, I realize that I'm not giving a talk to people who are in the field, but yet you are here, and I take it as a great privilege and a blessing. So I shall try not to overwhelm with too much jargon and technicality. Okay. If I do, please tell me. In all my life, especially in the area of my science and research, I've often felt that it was important to cultivate a sense of wonder. And I hope that's clear, to cultivate a sense of wonder. And I'd like to start with this quote, which comes from Neil Armstrong, of all people, not a scientist. It says, "Mystery creates wonder, and wonder is the basis of mankind's desire to understand." And I think that expresses a deep truth in each one of us. We are all curious people. Now, it may be true that curiosity kills the cat. But curiosity has caused our species to actually move beyond. And it is this which creates the wonder and for our desire to want to understand. And in the course of the last few thousand years, from the time when we started to count until when we started to look at the stars and to look at things and ask, are there patterns going on? And recognizing that it's possible to locate patterns, we have very fortuitously been given a tool or developed a tool that helps us to make sense as to whether there is a pattern or there isn't. And that is mathematics, which is the universal language, I believe, not only of science, but all endeavor and all learning. And if I may quote, I did not manage to write the name of this gentleman, but I don't think it would be a surprise if I tell you that this is Galileo Galilei. And he writes, the universe cannot be read until we have learned the language and become familiar with the characters in which it is written. It is written in the mathematical language, and the letters are triangles, circles, and other geometric figures, without which means it is humanly impossible to comprehend a single word. If anything that I would like to add, since the time of Galileo, we have added calculus, topology, all sorts of different fields of mathematics, each one designed to answer the question, is there pattern, is there symmetry, is there regularity? And if I may proceed from here, much of what we have learned in science, or more particularly in physics, has started off from abstractions. All of us, when we make models, we always use abstractions because reality is too complicated. So there are two abstractions that I'd like to look at today. One is the abstraction called a particle. And a particle is a geometric point imbued with a mass. Now, when we look at the Earth circling around the sun, we can treat the Earth as a particle. When we look at the moon circling around the Earth, we can treat it as a particle. But when we stand on this Earth, we cannot regard the Earth as a particle, although we may regard ourselves as particles relative to the Earth. So that is an abstraction, a concept that we use to start off. And another abstraction is the abstraction called a wave, which is an undulation of infinite extent. If we look at these two abstractions, we realize that they're quite different. A particle is localized in space, it is fixed. You can know precisely where its position is. But for that very instant, it is not moving. On the other hand, if you look at the wave is moving, but it has a pattern, it has an undulation, it has a frequency, it has a wavelength. But if you want to ask, where is there a particle within that wave, it's hard to say. In fact, it's impossible because it has an infinite extent. So from these two fundamental abstractions, all of science, of physics in particular, has developed. May I take you back to perhaps your school days and torture you with the Newton's laws of motion. For many of us, or I guess all of us, Newton's laws of motion is served up as a dish, 300 years old, cold dish, which we memorize and hope to try and use in some exam. And it's something we want to forget and to avoid when we don't have to anymore. But it's actually very exciting. It didn't come ready-made from anywhere, but came as a result of observations and came as a result of imagination and creativity. And it turned out to be right, which is why we use it now. The first one is a body at rest will remain at rest, and a body in motion will remain in motion unless it is acted upon by an external force. this wasn't always accepted. Approximately 2000 or so years ago, Aristotle would have said, no, the natural state of an object is to be perfectly at rest. Moving along in a straight line at a constant speed is not considered a natural state. And from that one point, physics could not progress for about 1,500 years, because the starting point was not fruitful enough. But Galileo came up with this, that it is equally valid to have an object moving at a fixed speed in a straight line to qualify as a natural state, just as it is to be perfectly at rest. And that allowed us to have Newton's second law of motion, which said that if motion is different from the natural state, that can only happen if there is a force applied to it. That force will give rise to something called an acceleration. And when we have two bodies interacting with one another, one body reacts on the other, and the other will react back on the other. From these three laws come the whole edifice, if you like, of classical mechanics, which has answered so many questions. For example, the motions of the planets around the sun, why there are tides on the earth, and how to understand where tides come from, and so many other things. In fact, with Newton's laws of motion, and also another law which is called the law of universal gravitation, which I will not go into the detail of, and if we know at a particular moment what the velocity and what the position of an object is, we can use the mathematics that Newton devised to actually predict the trajectory of the object throughout all time. Now, if you think about it, that's fantastic. I mean, knowing where you are and what you are moving at a certain point of time, knowing all the forces that are at work, you can actually play like playing a tape recorder, how the motion and the trajectory will be. And in fact, this idea was so startling that at that time it gave rise to a philosophical question. It says, if that is true, what Newton says is true, could it be that we have determinism, that there is no such thing as free will? Does it apply to our lives? Of course, when you think about it, we know that that's not the whole story. But seriously, determinism and a clockwork universe was considered one of the philosophies which were propagated because of the success of Newton's laws. Now, I do not wish to startle you, ladies and gentlemen, suddenly with this. The reason why I bring this is not that I intend to explain what each equation means, but basically to tell you that they arise out of electricity and magnetism. I think all of us at some time in our lives have played with magnets. You've taken two magnets and tried to force it together. You find it doesn't go, and if you turn the direction, it does. Or you might have played with electrical things, and those have been known for maybe 2,000 years. But through the efforts of many people, eventually somewhere in the mid-1860s, all that was put together and synthesized by this gentleman, James Clerk Maxwell. He put everything together, these four equations together, and discovered that as a byproduct of putting those four equations together, these equations predicted the existence of an undulation which moved at a very special speed. And it turned out, when people did the experiment, that this speed was exactly the same as the speed of light. And so basically it means that electromagnetic forces actually are the origin of light, and that synthesize electricity synthesize magnetism, and also synthesize optics, the complete field. And so when we turn on our, or when we sit down and we are looking at our handphones and we are getting the electromagnetic signals, well, we have the understanding of it. We have James Clerk Maxwell and all the other workers to thank for it. So this is the reason why I decided to show you this set of equations. From the work of Newton and Maxwell, there was a great deal of success in physics up to about the year 1900, when it was felt that, well, no new physics is there to be learned. And I quote you something which Lord Kelvin, Benjamin Thompson said, that aside from two clouds or two things that are spoiling the view, everything else seems to be fine. All that we needed to do was measure to greater degrees of accuracy. But it turned out that those two clouds in the horizon caused a great revolution in physics in particular and in science in the 20th century, and led to the creation of, one, the theory of relativity. Even if all of us do not understand what the theory of relativity is, I think we have heard of this term relativity, and immediately our minds would be linked to Albert Einstein. And if you have been watching the series on National Geographic every Sunday for the last 3 weeks, you will be seeing his life story and his life and loves. And the other cloud gave rise to the subject that I will talk about in slightly more detail, and that is quantum theory. But before I do go to quantum theory, may I take a few moments to talk about the atomic nucleus? Because this is the subject or the area in which I decided to specialize in after I finished my degree. If you ask me why I decided to go into this and not some more fashionable and interesting area, well, at the end of my undergraduate study, I was more interested in becoming a theorist. I discovered that I did not have the requisite sublime talents of the experimenter, the kind of fingers for designing experiments, of making the experiment talk to you and give you good results, you know. But I didn't know how to add and subtract and multiply and divide and integrate and differentiate, and I thought, yes, I'd like to be a theoretical physicist like Albert Einstein. But there's where the similarity ends. But the atomic nucleus was something that I was interested in because of one of the teachers in the physics department at that time, Dr. Lolo Marangkup Panggabean, who liked to point at us with his long ruler, and I found that I could answer his questions. So that gave me some confidence. So for that flimsy reason, I decided that I would like to study atomic nucleus. And the field of atomic physics, atomic nucleus, is actually started by this gentleman, Lord Rutherford. And Lord Rutherford is the discoverer of the alpha particle. But aside from that, he is the one who discovered the whole idea of the atomic nucleus. This quote is from him. It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you launched a 15-inch shell at a piece of tissue paper and it came back and hit you. Now, if you recognize how highly improbable that would be, that was his sense of surprise. Why did that happen? He did this experiment where there was a radioactive source giving out some alpha particles aimed at a very thin foil of gold, and he had instructed his co-workers and students to just make measurements mainly make measurements near the front. He was expecting that all the particles would go straight forward. But you know, one day, somewhere in that experiment, he asked his co-workers, why don't you try and see whether you detect anything near the back, where things bounce almost back. Now, most people would have said, obviously it won't happen, so why bother to measure? But this is serendipity. And there is a phrase that I like very much: chance favors the prepared mind. I think it was said by various people. August Cocule, I think, might have been one of those. I learned it from Under Siege 2, where the villain liked to quote this phrase. But I found later that it had been used by other people. And because he had a mind, Lord Rutherford had a mind which was prepared, he could immediately grasp when he saw that 1 out of every 8,000 alpha particles bounced back. 7,999 particles went straight through. That was the uninteresting part. But the one which bounced back, that is the most interesting part. Now, why am I telling you this? Because all the big experiments now, finding the Higgs boson and so on, all of them are of the same kind of thing. If you imagine we want to find a very rare event, you have to have a huge equipment in order to do that. You have to expend huge amounts of energy and throw away all the things which are not interesting just to find the little thing that's interesting. And the reason why that is so is because of quantum mechanics. Now, what's so special about quantum mechanics? Well, I suppose at its heart, what's special about quantum mechanics is what we call the wave-particle duality. If you recollect, I mentioned the two abstractions of wave and particle. And I kind of implied that those two were mutually exclusive. That when you have a particle, you can't have a wave. When you have a wave, it's not a particle. Yet, surprisingly, quantum mechanics admits wave-particle duality. If you look at light, there are times when light would manifest wave properties. There are times when it would manifest particle properties. And it turned out that it's true for all matter as well. Everything manifests wave and particle properties depending on the kind of experiments we do. And so I just would like to show you this. Imagine if you have sunlight coming through a little slit here, and then after that proceeding through two other slits, we get this kind of characteristic pattern which is called an interference pattern. You might remember this from your physics class in secondary school, you know, where all of us learned this sometime. But if instead of a beam of sunlight, we just took one photon at a time and send it in slowly, one, then another, send it through the same kind of arrangement, you will find initially there's nothing. But then over time, you would see a pattern starting to form, which is exactly that interference pattern. And if you're wondering, how did those individual photons arriving one at a time how did they know that they would wind up giving an interference pattern? Well, the answer is they didn't know. But because of wave-particle duality, that is what happens. And wave-particle duality is intrinsic to quantum mechanics. And because of wave-particle duality, we have something called the Heisenberg's uncertainty principle that says that it is impossible in principle to know at any given moment the exact position and the exact velocity of an object. If you know the position exactly, you lose all information of the velocity. That's a pure particle. or if you know the velocity exactly, you lose all information of where it is. That's a full wave. But if you're prepared to compromise and say, well, I'm prepared to know where the particle is to within some degree of uncertainty, then there is hope to also measure the velocity to some degree of uncertainty. And that is the uncertainty principle of Heisenberg. In fact, this also created a philosophical question. Is all life uncertain? Is all life uncertain? So whatever you want to do, oh, I'm uncertain, because Heisenberg says uncertainty principle holds good. Well, Heisenberg uncertainty principle holds good in physics, but in our day-to-day life, I'm afraid we can't blame Heisenberg for our own, contrary ways. We are completely responsible for that, not Heisenberg. And I'd like to introduce, I think, the only equation I want to spend some time on, and that is the equation of Schrodinger. Schrodinger and Heisenberg were the creators of quantum mechanics, the first two creators of quantum mechanics. Schrodinger was working on a paper by de Broglie on wave-particle duality, and he presented it in a seminar in Berlin. And as he presented this paper, Debye, a physicist, said, this is, what you're telling us is actually quite useless. If you say that there is a wave property, there ought to be a wave equation. Debye made the comment and didn't think to follow up on it and work. Schrodinger took it seriously when he went for a holiday up in the mountains, in ski slopes. He brought along a physics book, mathematics book, and a lady companion. And in the few days of bliss, working on physics and physique, he came up with this equation in 1926. Okay, and that equation was able to actually solve a problem, a fundamental problem of what's known as the hydrogen atom. The hydrogen atom is made up of a single positively charged proton and electron going around it. To solve that problem using quantum mechanics, Schrodinger solved that equation, got the results, and showed that it predicted that the electron could only exist in certain very limited states. What's labeled here as n equals to 1 and 2 and 3, those are the solutions. Now, a few years ago, 3 to 4 years ago, they actually measured and managed to show these clouds and distribution of the electrons. If you bear in mind that this prediction was in 1926, and this observation is 2013, we see, how it has been borne out. But of course, it has been borne out many, many times, okay? But direct observation has only been possible in the last few years. Now, how do we go about solving this, or should I say, what does this equation actually try to do? Well, it tries to describe the time evolution of the wave function. This is the wave function under the influence of interactions contained in this operator or this Hamiltonian. For the interest of not creating problems, I'm not going to say what kind of interactions they are. All that matters is that this is a machine. Okay? If I know what the initial state is, and if I know what the interactions are, this equation allows me to predict what the state would be at any given point of time. Okay? Now, the most significant thing in this equation is this quantity here, h bar, which is called the reduced Planck constant. It's a very small quantity, 10 to the power of negative 34 joule is an energy unit, and seconds is time. If this value, h bar, had been exactly 0, there would be no quantum mechanics. If this value had been exactly 0, the mechanics of Newton would have been perfectly right. But because it is small, tiny, but not 0, and that is the point, that meant that whenever we went to scales which are small enough, the difference will be seen. And that's why we have quantum mechanics. And the object that we want to look at is this quantity, that is this wave function squared. The reason why we need to square it is because that wave function is a complex quantity. It has a real term and an imaginary term. And the absolute value gives us a measure of the likelihood, the probability of finding the particle in any given particular state. Now, rather than do that, I thought I'd like to show you maybe a sampling of what it means to solve this equation. Supposing we have a parabolic interaction or parabolic potential. This is our initial wave, okay? Now, if you imagine, so this thing keeps falling down, but if you imagine that we have a pendulum, we know how the pendulum will move. It will be very slow at the end, very fast in the middle, and it'll be slow at the end, and it'll stop at the end. It'll do this kind of oscillatory behavior. We know that very well from mechanics. But if you try to solve it using quantum mechanics, we begin, look at the black curve. Don't bother about the red and blue ones, because that is looking at the real and imaginary part, which we don't have to look at. But as you can see, there is an oscillation going on. As we solve the Schrodinger equation, we find that that pattern is just moving from side to side, slowing down at the side, speeding up in the middle, slowing down at the other side. Now, I realize I'm saying things in a way that probably will tend to put people to sleep, and I apologize. I've been known to do that to my students. If we look at this other example, there are two barriers here, okay? One barrier is shorter than the other. One barrier is higher. If we allow this pulse, these are two identical initial pulses. If we allow them to move, okay, observe what happens to the blue one. The blue one, you'll find that the pulse actually split into two. One part of the pulse went forward, one part of the pulse went backward. In other words, there was a probability that part of that pulse could actually penetrate the barrier and go forward. And that is the explanation of why we have, for example, alpha particle radiation. When we have a nucleus, the alpha particles inside are just moving along, and if the probability is right, it can just tunnel through. And so tunneling is a feature of this process called quantum tunneling or radioactive decay. Now, okay, I do not want to spend too much time beyond this and test your patience. But basically, if you think about it, we have an atom, okay? We have this as an atom. Inside the atom, we have nuclei, and imagine this is the nuclei. Now, I must tell you that this is not to scale, but it's just to show you what's inside. So you have the atoms. Outside are the electrons. Here they are. And then inside is the nucleus. And the nucleus is made up of a neutron and a proton and so on. And what we know now is that the neutrons and protons are actually composite particles, that they are made up of things even smaller called quarks. I'm sure you have heard of this term quarks, yeah? And if to get some idea of the scale, if the protons and neutrons in this figure were 10 centimeters across, which is about that, okay, then the quarks would be less than 1/10 of a millimeter. You can imagine how small that is. and the entire atom would be 10 kilometers across. So if you imagine that, if you imagine that you got into your car now and drove at the sedate pace of 50 kilometers per hour, then after traveling in your car straight line for 12 minutes, that would be 10 kilometers. And that would be the size of the atom relative to the size of the nucleon. So in between every nucleon and the whole atom, there's a lot of empty space, which is what Democritus said about 2,000 or so years ago, that the whole of matter is composed of atoms and the void. The first person who realized this was Rutherford after he did that experiment. And after he realized that the nucleus was so small and there was so much empty space, the next day when he woke up from bed, he was afraid to put his foot on the floor. Because he thought if he put his foot on the floor, because there's so much empty space, he might fall through the floor. Of course, we know that won't happen. But it's something like if you have ever watched the Roadrunner cartoon. Wile E. Coyote chased after the Roadrunner. Now, and Wile E. Coyote runs across or runs off the edge of a cliff. So long as he did not look down, he kept right on going with no problem at all. But the moment he looked down and realized that there was no floor under him, down he went. So in a reverse way, Rutherford was afraid. At that first instant of discovery of the void, what if would he go down inside? But of course, science says it won't happen. Well, I will not talk too much about things smaller than a nucleus. It's beyond my own competence and my own specialization. But just to say that in science, we've looked at scales, the size of the celestial bodies, and then our own sizes, down to the size of a cell, down to the size of an atom, down to the size of the nucleus, and right down here to Planck's constant, the value 10 to the power of minus 34. And this ruler here is in a logarithmic scale, so it's not a straight line like this. Okay, it's logarithmic scale. And on the celestial and human levels, the mechanics of Newton works perfectly fine. But once it comes down to the atom, quantum mechanics starts to hold true, as we saw just now when we were looking at Schrodinger's equation. As we go even smaller, we start having to look at quantum field theory, where where it is applied not to particles but to fields. And right now, the buzzword I'm sure people would have heard of is string theory. Now, whether string theory is true or not, nobody knows. I've put it in a slide called speculations. And Edward Witten, who is, some people consider Edward Witten the successor of Einstein at the Institute of Advanced Study in Princeton, has many things to say about string theory. And he says, quantum mechanics brought an unexpected fuzziness into physics because of quantum uncertainty, that is the Heisenberg uncertainty principle. String theory does so again because a point particle is replaced by a string, which is more spread out. Well, if you understand that, you probably understood more than me. But the reality of it is that the idea is, as we go down to the very small, quantum field theory starts looking at points and particles, but string theory says no, not looking at points, but looking at more extended, like your rubber band, Is it true? Nobody knows. It's speculations. But that's the fun of science. We always have speculations that in time to come will have a chance to either be proved true or to be disproved. I would like to go to this last section of my talk, back to nuclear physics again. This chart is the chart of nuclides, where you see the number of protons and the number of neutrons. I only would like to draw your attention to the part of it which is black. The part of it which is black are all the isotopes which are stable isotopes. And you notice that as we go along up to about lead, that's about near the end of where things are stable. Beyond that, it starts to go to uranium and all those other stuff, which is not stable, basically. When I first started out as a master's student, my supervisor, whom I regret could not be here today, Emeritus Professor Lau Kam Sang, because he suffered a fracture not too long ago. He was telling me about the search for super heavy nuclei. And I thought this was fantastic, super heavy nuclei. And if you look at the nuclei which are stable, you have oxygen, that's over here, Z equals to 8. We have calcium, we have nickel, we have tin, and of course the highest is we have lead. So the question is, way up here, are there some more stable nuclei? If there are, then that means there can be some new materials. I don't know if you watched Iron Man 2. You can tell from my some of the things I say that I watch a lot of TV. Iron Man 2, Tony Stark was suffering because of some poisoning. And he had to get a new element and replace it in his chest. And that new element would not poison him and give him the power. Of course, if you believe the story that he worked all by himself in the basement of his home and he managed to create that element, well, you have to suspend disbelief, but that's what he did, a super heavy element. So that's science fiction. So again, in this graph, as you go along, we are looking for maybe the mountains like the Himalayas, where you might find super heavy elements. Well, this is the latest chart of elements. You might notice that there are many more elements than when we were in school. When we were in school, probably it was only about 900 or something like that. But now it's gone all the way up to 118. Okay, the most recent one is 118. And the speculation is if they manage to go up to 120, they will begin to get super heavy elements. So maybe not so far away, and maybe more likely to happen than Iron Man. But I find that very exciting. And I'd like to close by quoting the physicist, the nuclear physicist, and not only nuclear physicist, Eugene Wigner, who received the Nobel Prize in 1963 together with Maria Goeppert-Mayer and Jensen, and for nuclear physics work. And he talked about the unreasonable effectiveness of mathematics. It's a famous article, that the famous speech he made. And I'd just like to quote a sentence from it. It says, "The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift, which we neither understand nor deserve." And he goes on. "We should be grateful for it and hope that it will remain valid in future research, and that it will extend, for better or for worse, to our pleasure, even though perhaps also to our bafflement, to wide branches of learning." And I think from the time he gave this talk in the 1960s to now, we've seen it to be true. In biology, for example, mathematics has begun in bioinformatics to become more and more important, even in linguistics and in other areas of endeavor. So the language, the universal language of mathematics is being brought and enabling us to answer questions and to find patterns underlying reality and to give us this sense of wonder. As I end, may I thank the University of Malaya. I mean, I was here from 1977 until 1988. It took me a long time to graduate. But I want to thank God for it, and the teachers, especially in the physics department, who helped me. And also, I want to thank colleagues here from the University of Malaya, and also from Institute of Mathematical Sciences, with whom it's been my privilege to serve for 23 and a half years. I would like to thank the Vice Chancellor and the senior management of the university for the opportunity to serve in admin for 7 years. It gave me a different perspective from that of a teacher, and I value it. But after all that time, I think I still want to come back and teach. I want to thank all my friends and colleagues from my school days who are here, and also for my classmates. As we go older, we seem to set up groups so that we can meet and talk, even though, so that was a good thing. I want also to thank my supervisees, two of whom are here. A surprise to fellow PhD students in the physics department whom I didn't expect to see here, Dr. Ignatius Rasya and Dr. Malini, all the way from Singapore. Didn't expect you to be here, but thank you for being here. I want to thank my parents, my late parents, who didn't understand what I was doing but supported me nonetheless, who loved me nonetheless. I want to give thanks for my family, my wife Agnes and my little boy Fidel, who should have been here but wouldn't have been able to sit quiet through my long talk. And finally, oh, he is sitting quiet. Oh, he's sleeping. I didn't know. Well, praise God. And finally, I want to thank the Lord God Almighty, who was, who is to come, the God who created all things and allow us to enjoy life, enjoy the things that we are doing, and to give this opportunity for me to end my official career at University of Malaya with this last inaugural lecture. Thank you very much.
A bliss, huh? Ladies and gentlemen, I would like to call upon Professor Nosada to conclude today's lecture.
Thank you very much. Thank you, Prof. Bernie. It is a very interesting and inspiring talk. I wish you had been my teacher in quantum mechanics, actually. But anyway, to summarize Prof. Bernie's talk, Prof. Bernie today spoke on the topic of quantum theory and atomic nucleus. And he began by expressing his conviction that science is a journey of discovery driven by curiosity. Hence, it is a deeply creative activity, and it is vital to cultivate the sense of wonder in research. He also spoke about mathematics as universal language of science, how it carries logic in its manipulation, and how one uses mathematics to make predictions, which can then be checked against experiment. Prof. Bernie also talked about fundamental abstraction of particles and wave, and explained how this abstraction were respectively used the formulation of Newton's laws of motion and Maxwell's equation of electromagnetism. He outlined how these abstractions were integrated together in quantum theory, which built upon the particle-wave duality, and also briefly discussed the time-dependent Schrodinger equation, which is widely used to model the evolution of a quantum system with time. He just didn't have time to talk about the cat in the box. Prof. Bernie also elaborated on the atomic basis on matter, in which the atomic of every element consists of a nucleus comprising protons and neutrons surrounded by clouds of electrons. While the electron is an elementary point particle, the protons and neutrons are made up of still more elementary constituents. And the constituents and forces of interactions between them are currently being investigated and using the advancement in quantum theory and string theory. And if anybody is also a fan of Big Bang theory like me, we'll hear a lot about string theory from I forgot his name now, although I'm a fan. Anyway, Prof. Bernie finally talked about some areas of research in nuclear physics, and in particular focus on the search for super heavy element of the periodic table, which holds the promise of being a stable new element. Einstein once said, "Look deeper into nature and then you will understand everything better." So I think Prof. Bernie has actually helped us into looking, maybe understanding a little bit more about nature through the quantum theories and quantum field theories. And I think we're a little bit more richer for this. Thank you very much. And in keeping with the tradition of inaugural lecture where there is no questions, we are not going to allow any questions, but we would like to thank Prof. Bernie in our usual manner, please. Thank you.
Thank you, Prof, for chairing this lecture. Before we end today's inaugural lecture, it's my pleasure again to invite Professor Bernardine Wong to come on stage to receive a small gesture of appreciation from the Institute of Mathematical Sciences, University of Malaya. Professor Ainun. Thank you. Once again, I would like to take this opportunity to thank Yang Bahagia Professor Dr. Nosada Abdul Rahman, the Deputy Vice Chancellor, Research and Innovation, the Dean of Science, Prof. Zana, and the Management Faculty of Science, Professor Wan Ainun, Institute of Mathematical Sciences, and her staff, hardworking staff, International Corporate Relation Office, students and staff of University of Malaya, as well as all the distinguished guests, young and old. Sorry. Made time to be in part in today's inaugural lecture. With this, we have reached the end of the inaugural lecture. On behalf of University of Malaya, I would like to express our gratitude and also apologize if there had been any shortcomings from our side in organizing this lecture. We'd like to invite all of you to have some, I don't think it's light refreshments. I saw roti jala, so which will be served just outside this auditorium. Ladies and gentlemen, once again, our deepest gratitude for your presence and have a pleasant afternoon. Thank you.